So today I'm going to present about how training spatial cognition enhances mathematical learning. This is a project I did with my PI Torkel Klingberg, and I am a PhD student in the Department of Neuroscience in Karolinska Institute. So first I'm going to start off with just some brief intro into mathematical learning. So we know that cognitive abilities correlate with math performance, for example, nonverbal reasoning, mental rotation, and working memory. Yet these abilities also correlate with the subsequent development of mathematics and can predict the development of mathematics. So say if we measure visuo-spatial working memory in an 8-year-old, it will be able to predict variance in mathematics in that child when they are 10. Now, one thing that all of these domains have in common is that there are spatial abilities. Spatial abilities defined by Lohmann and Carpenter and Just in the 1980s involve at least 3 core aspects. That is the creation of an internal spatial representation, its maintenance, and then its subsequent manipulation. Possibly due to the tight link between these spatial abilities and mathematics, this has led researchers to ask if these can be improved. Now we know mental rotation abilities can be improved through a really good meta-analysis by Uttal and colleagues in 2013. Furthermore, we know that training visuo-spatial working memory leads to improvements in visuo-spatial working memory, as you can see in this graph right here of meta-analyses. And lastly, nonverbal reasoning seems to show, there seems to be preliminary evidence that if you train nonverbal reasoning in children, that it will increase their nonverbal reasoning abilities. So possibly due to the fact that we know these spatial abilities can be improved, and we know that they're crucial for mathematical thought, this has led researchers and educators to encourage the training of spatial abilities in children, especially in children in primary school. For example, the Ontario Ministry of Education has released a pamphlet paying attention to spatial reasoning. But this is a different, now we have a bit of a logical leap because we know that spatial abilities can be trained. We see they have a tight relationship with mathematics. But this logical leap is, does the improving of spatial abilities in turn improve mathematics? That is it causal in nature? Luckily, a lot of researchers have looked at this, in particular for rotation training. Here are a lot of studies. So the first study was by Sheng and Mix and colleagues. Oh, sorry, just Sheng and Mix in 2014. And they trained 58 7-year-olds on one 40-minute rotation task. And then they had an active control of literacy training, and they found an effect. Yet this effect could not be replicated by Haas and colleagues 1 year later, in which they had a much larger rotation intervention. And then as you see, going back and forth throughout the years, there are some studies that find this effect of transfer to mathematics and others that do not. And there's a bit of a mix here, and they're not all leading to finding effects, and they're not all leading to not finding effects, and it's quite unclear. Now, the story with visuo-spatial working memory is also similar. So I'm going to focus on the 2 largest studies in children. I'm focusing on these 2 because they're very large. They're in the same age range, so they're in 7-year-olds. They have the same training, so they have CogMed visuo-spatial working memory training, and they're also for the same duration, 5 weeks. But even more crucially, they look at long-term academic outcomes. So does this visuo-spatial working memory intervention affect mathematics or reading or another academic outcome 2 years later? So the first study is by Roberts and colleagues in 2016. And they looked at a low working memory population, 450 of them in Australia, and they found no effect 2 years or even 1 year after the intervention. In contrast, Berger and colleagues a few months ago found an effect in a typically developing population of about 600 7-year-olds in Germany. And they looked at arithmetic, geometry, reading, and Raven's IQ, and they found effects within the range of 0.2 to 0.3 in Cohen's standard deviations. And if you look right here, you can see that the effects for geometry gradually increased over time. Now, a really cool thing about this study is they followed up the children 4 years later. And in Germany, children are put into secondary education tracks that then, and there's one called gymnasium, which then naturally leads to tertiary education and to college. Of course, from the other tracks, you can also go into college, but this is the one that primarily leads children into college. And they found that the children that had visuospatial working memory training had a 16% higher chance of going into gymnasium, which makes sense. If these effects are true, we would expect it to impact a real world outcome, like going into gymnasium. So this naturally leads us to the question of why there are so many discrepancies in the literature, especially in respects to far transfer and mathematics, from spatial abilities to mathematics. So there's so many discrepancies, I would argue, because of a lot of heterogeneity. So there's different training methods, different outcomes in different populations. On top of that, the earlier studies lacked blinding and proper controls. And on top of all of this, there's inadequate statistical power. And now we know that if we are running an underpowered study and we find significance, the effect size by definition must be overestimated. This phenomenon is known as winner's curse. And this year it was awarded the Nobel Prize in Economics. So yeah, the literature is inconclusive to say the least. Yet if there is transfer, and again, that is a big if, and transfer from spatial abilities to mathematics, what would that mechanism of transfer be? Well, there are two mechanisms of transfer I'm going to highlight here today. The first is manipulation, and the second is maintenance. So say if we were to contrast rotation training to visuospatial working memory training, and if manipulation really matters for the transfer to mathematics in children, we would expect rotation training to be more effective than visuospatial working memory training. And conversely for maintenance. So if maintenance is the primary road of transfer, then we would expect visuospatial working memory training to be more effective than mental rotation training. So this leads us to the outstanding questions we are going to address. The first being, does spatial training impact mathematical learning? And if so, is mental rotation or visuospatial working memory training more effective? And the second question is a bit different in nature. It is, are there inter-individual characteristics that predict the optimal type of cognitive training to enhance mathematics? So this is pretty much, if there is a child that is struggling at rotation problems, maybe they will differentially benefit from rotation training rather than visuospatial working memory for their transfer to mathematics, because that is the spatial domain in which they are struggling in. So these are the two questions we're going to address today. But first I need to describe some background. So this is a study Nemi and colleagues published in 2016 from my previous supervisor, Federico Nemi. And he looked at 308 6-year-olds. And he had a pretty standard randomized controlled trial design in which there was one group, as you can see, it's not giving me the thing. Can you guys see my cursor? Well, in the left-hand corner here, we see active reading training. So some of the children only had reading training, and it was only active reading training. Then another group had reading and visuospatial math training. And then lastly, there was a group which had 100%, 50% of the time was visuospatial working memory and 50% was math. So pretty much the active control was divided around. And then there was one group in which had full active training. And then the outcome was a composite math measure of addition and subtraction missing term problems, and then the WISC verbal arithmetic. And the training tasks look like this. So it was 5 weeks of training. The number line tasks, the mathematics, started with basic number line and then progressed to addition, subtraction problems, and fractions and decimals. And then there were 6 different visuospatial working memory tasks. And now this was in collaboration with Cognition, the nonprofit Cognition Matters, which has a freely available app called Vector, which is designed in tandem with our lab. So moving on to what it looks like. So this is what the app looks like. So first the child can choose their avatar and how they want it to look like. And then they will move on to the number line training. So in the beginning, it guides the children. So it shows them where they should do and what they should do. And then slowly these cues go away. And eventually it adds up to being addition and subtraction problems on the number line. So quickly moving on to the results for Nemi and colleagues in 2016. The first was an effect for number line training. So he found a significant effect of number line training on mathematical improvement, as you can see from the green group here, where there was the most gain from working memory and number line training. Yet there was no main effect for visuo-spatial working memory, even that this was the group that improved the most. So this effectively shows that our mathematic training is effective, essentially, at training mathematics, and that there could potentially be a case for visuo-spatial working memory, yet again, he found no significant main effect. So moving on to our design. Our design, we had no active recruitment, but it is very ecologically valid in so that the implementation was entirely up to the teachers, and the app logged out automatically after the child did 33 minutes of training per day. And then within the first week, all the children completed identical training. So they had 50% of the time math. Then they had visuo-spatial working memory. And then we added two types of tasks. We added nonverbal reasoning, and we added rotation. And within rotation, we had two rotation tasks, 2D mental rotation and Tanagram. And the 2D mental rotation task looked like this. Is pretty much a standard 2D mental rotation task. Now moving on to the Tanagram task. It's again also heavily taxing manipulation over maintenance. And you can see that this actually involves physical manipulation from the children. Now moving on to our design. So everyone within the first week did the exact same training, and then they were divided into different training plans. So the default plan was from Nemi et al. In 2016, where the children either did 50%, every child did 50% math, but in the default plan, they did 50% visuo-spatial working memory. Then we had a plan rotation where we took away 13% of that time of visuo-spatial working memory training, and we substituted it for rotation. Then we had another rotation heavy where 30% of the time was rotation rather than visuo-spatial working memory. And then we had another two where we put nonverbal reasoning into the mix. So one where we added nonverbal reasoning, and then one mixed plan where we had 10% of the time nonverbal reasoning and the other 20% of the time rotation. So everything here is a very high bar because we're taking out visuo-spatial working memory training and then adding different types of spatial training, say rotation and NVR. Of course, there is the null, and the null would be that none of this matters at all. If spatial cognitive training does not transfer to mathematics, we would expect absolutely no difference between these training plans when the children are randomized after the first week. So now the good thing about this design is it allows us quite neatly to answer the questions we were interested in. So going back to those, does spatial training impact mathematical learning? So we randomize the children into varying groups after a week, which would allow us to answer this question. And then furthermore, we take out some visuo-spatial working memory training and put in mental rotation training, allowing us to answer which one had the effectiveness of those two. And then our second question on, are there inter-individual characteristics that predict the optimal type of cognitive training to enhance mathematics? We have an identical first week in which everyone does the same spatial training. So from that, we can get their baseline levels prior to their randomization. Now moving on to how we tested mathematics. So this study was entirely remote. So the tests had to be self-administered. We had addition tests, subtraction tests, and number comparison tasks that were self-administered. And the baseline, T1, was on the third and the fourth day. Then we had a second time point at the 5th week, and then we had a third time point at the 7th week. And we combine these into strict measurement invariant CFA. This doesn't really matter that much, but it essentially means that we're confident that we're measuring the same construct over time. And then furthermore, in 100 children, we measured them with an experimenter, and one of the tasks was different. So sadly, we didn't have a number comparison task. So we used the whisk verbal arithmetic, which changes the invariance of the factor and makes it a different thing. But we still found a 0.7 correlation with these self-administered tasks versus experimenter-administered tasks. So we included 6 to 8-year-olds with 7 weeks of training. We had an ending sample of 17,648 children, and this was over 2.5 years, so 5 semesters. And each of these children completed an average of 5,000 trials. Here you can see their mathematical improvement. And after 5 weeks, there was 0.45 standard deviations of change, and after 7 weeks, there's 0.56. Now, of course, this includes variance of test-retest effects and natural development, and of course, of the mathematical training itself. Now moving on to the training tasks. Performance in the first week correlated with baseline mathematics, as we would expect. So here you can see in this lower line that the mean level of number line in the first week had a high correlation with baseline mathematics, as we would expect. The same for visuo-spatial working memory, rotation, 2D mental rotation, and then NVR as well. Right now, it looks like NVR is correlating less, but that's just because of the task design and our nonverbal reasoning. And this, after the first week, the variance expands, and then this ends up being in line with the rest of the tests. Furthermore, all of our training tasks showed significant improvement over 7 weeks, as we would expect. And this is what the training curves look like. So here you can see on the x-axis, the number of days. So we included 36 days. And then on the y-axis, the mean level for the number line task. And then for visuo-spatial working memory, it looks like here. We had so many subjects, so these are training curves, and the dots are the median. But they are represented with density instead of actual subjects, because we had so many subjects. And then this is what I was talking about, the variance being constrained within the first week and why that correlation is a bit lower. So moving on to our analysis. Does spatial training impact mathematical learning? So if it doesn't, we're not going to find any difference between our randomization after the first week. It's not going to matter. So we took a 3-pronged approach to answer this question. And they're all answering the question. It's all answering the question, just different ways of going at it. So and pretty much in order of conservativeness and the amount of assumptions you're willing to make. So the first is coding the training plans categorically. So that's pretty much acting as if there is the training plans are independent of each other, even that there are ones with varying amount of rotation and varying amount of NVR. So to do that, we added 2 terms, one with the amount of rotation and one with the amount of NVR. And then lastly, we did an analysis where we just coded for the amount of minutes in each task. And we used linear mixed effects models, of which an AIC difference of 8 was meaningful, with a random intercept per subject and a random slope per testing occasion. So moving on to the results. Training plans coded as categories improved model fit significantly and to a decent extent. So there was an AIC difference of 24. NVR showed the most improvement, while rotation heavy showed the least. So you can see that right down here with the coefficients of the interaction with time, and then NVR right here. This dashed line here is Nemi et al.'s 2016 training program with 50% visuo-spatial working memory. And then here's the rotation heavy doing significantly worse than that plan. And this is the NVR doing significantly better. Now, there was very little difference between these plans, yet we do believe them to be meaningful, and we will get into this into the discussion. So moving on to the second analysis, if we just coded for the amount of rotation, the amount of NVR, therefore the intercept is again the Nemi plan, we found a meaningful model fit improvement. And then lastly, NVR showed the most mathematical transfer while rotation had the least. And crucially, our 2 rotation tasks similarly did poorly in comparison to visuo-spatial working memory, with some tasks being 2 to 3 times more effective. So now I'm going to pivot a bit, and I'm going to discuss the second point we're interested in, that is baseline characteristics that might predispose children to a certain type of cognitive training. So the way we looked at this is our dependent variable was math improvement, and then we had independent variables of performance, so the mean correct level in the first week before they're randomized, and then the accuracy, so the correct trials divided by total of number line, visuo-spatial working memory, rotation, and NVR. And then we interacted these with the amount of time that each subject did afterwards. So after this first week, when they get randomized. That leaves us with 3 models, one for visuo-spatial working memory, the time of visuo-spatial working memory interacting with these baseline indices to predict mathematical improvement. Another one with NVR and another one with rotation. So yeah, this analysis, I just previously showed you that rotation training was not more effective than visuo-spatial working memory, yet there could be some characteristics and some subpopulations of children struggling in rotation, which then benefit from the rotation training. Unfortunately, we did not find this. We found no interactions. We also controlled our false positive rate because there are quite a few interactions going on here in 3 different models using FDR correction. And we did not find rotation training to interact with baseline performance, the time on rotation training to interact with baseline performance. We did find significant interactions for baseline performance of working memory and baseline performance of NVR. So here you can see on the, so what this graph is on the Y, we have performance improvement in math. And then here we have baseline performance of working memory. So this is 1.5 standard deviations below the mean. This is the mean. This is 1.5 above. And then the colored refers to the amount of minutes of visuo-spatial working memory training. So what we're seeing here is a classic Matthews effect in which the children that have the highest baseline working memory differentially improve by having more visuo-spatial working memory training, which is, yeah, it's just what we find in our data. It's a bit sad, of course, because if you train children in visuo-spatial working memory, you would hope that that would try to catch up some of the deficits, but that's not what we see in this sample. Yet we do see this for baseline performance of NVR down here, where again, it's the colors are representing the minutes of NVR training, and then this is the baseline performance in NVR, and we see a catch-up effect for mathematical transfer. So the baseline performance of NVR is interacting with the amount of NVR training to predict mathematical improvement. So now going into a more general discussion, we showed that taking the amount of spatial training into account mattered, and changes of 30% of the content resulted in an 11% difference in mathematical transfer. Showing that cognitive training, this is essentially showing that cognitive training has far transfer to mathematical learning. It is also adding evidence for maintenance over manipulation as a road of transfer to math. And then it is also, and then lastly, we also see nonverbal reasoning to be more effective than rotation and more effective than visuo-spatial working memory. But there's an asterisk there because it's more effective than the last 13% of visuo-spatial working memory, and we don't have a group where it's only NVR and only visuo-spatial working memory. So now on to the far transfer controversy. We find an effect of visuo-spatial working memory training on mathematics. We find that children with higher working memory benefit from more visuo-spatial training. Now, this could be a potential answer for the discrepancies on far transfer. So remembering the two largest studies to date in 7-year-old in this age range, Roberts and colleagues was on a low working memory population, and they did a power calculation, and their power calculation was based on a Cohen's d of 0.3. And now if we expect a Cohen's d of 0.2 or 0.3, basing this off what Berger and colleagues found in a typically developing population, and then if we take into account that those with the best working memory are showing differential gains, then you would need a lot more subjects in the low working memory population to find an effect. So this could be a potential answer for the discrepancies on far transfer. So now quickly onto how much do children change. So what we can because we need to benchmark how much an effect size is. With these large samples, we can easily get significance, yet it can be meaningless. In this case, this is not one of those cases, and I will now get into some effect size benchmarking. So we can look at 1 year of schooling and development. A study by Bloom and colleagues does this for reading and mathematics. Here I plotted mathematics. So you see the grade transition, so from preschool to first grade, from first grade to second grade, and then you see the mean of 6 mathematical tests. So for our age range, it's about 1 standard deviation, which is a lot. But of course, if you're going to have an intervention, I mean, how much do you expect your intervention to match up to an entire year of schooling, but not only schooling, also an entire year of development? We can also look at how much schooling increases IQ, and Stuart Ritchie found it to be around 3.4 IQ points or 0.2 standard deviations. Then there is also a study recently that looked at 2 months of COVID school closures in the Netherlands and found it to have an effect size of 0.08 standard deviations. Yet importantly, their conclusion was that these results imply that students made little or no progress whilst learning at home, because the learning loss was almost equivalent to the exact amount of time they were not in school. And then lastly, looking at the Educational Endowment Foundation, a nonprofit in the UK, we see that the average of 141 of their randomized controlled trials, which are pre-registered and usually have adequate sample sizes, have a mean effect of 0.06 standard deviations. So there's not really that much change happening. And this has led to a reassessment of effect sizes and the importance of repeated cumulative small effects and that they matter, which was pointed out by Abelson in 1985. There's also a really good article recently by Funder and Ozar on evaluating effect sizes in psychological research, sense and nonsense. And lastly, there was a symposium organized by the NIH for the ABCD, which should be online shortly. So now going back to our study, some considerations. Everything is active. We can't estimate the absolute effect sizes of spatial training because we are taking visuo-spatial training out and then putting in rotation. So this is an extremely tough control, of course, because everything we put in, we expect to have an effect on mathematics. Then lastly, we can't estimate the impact of mathematical training. Because this was a freely available app, we did not really want to mess with the mathematics portion because in good faith, the teachers are using it. And then lastly, we had an identical first week of training, and this allowed us to get the estimates of these baseline interactions. Yet crucially, it also means everyone did some rotation training, everyone did a little bit of NVR. Lastly, with the take-home messages, the study adds evidence in favor of the view that cognitive abilities are malleable. And we expect that training on a particular skill is the most time-effective way to improve test results. So I'm not trying to argue here that we should just forgo mathematical training and have visuo-spatial working memory training instead. The fact of the matter is that this study is a proof of principle on far transfer. And given the wide range of areas associated with spatial cognition, including not only other fields of mathematics, but also science, technology, and engineering, it is possible that training transfers to multiple areas, which should be included in any calculation by teachers and policymakers of how time effective spatial training is relative to training for a particular test. And finishing up, I would like to thank you for your attention. I would also like to thank Torkel Klingberg, my PI, Rita, another supervisor of mine, Bruno and Dawe, which are postdocs in the lab, Dawe in particular, because he collected the experimenter-led tasks in those 100 children where we could find the correlation between these online administered tasks and experimenter-led tasks. And also David and Jonas Beckman, which helped develop the app, and of course our funders. Thank you very much. I realized I went a bit quickly because I mistook the time of the PowerPoint with the actual time. So if you have any questions because I went a bit quickly, just don't hesitate to ask. Thank you very much.
Thank you so much, Nick. Very interesting talk. Yeah, so we have plenty of time now for questions. So if you'd like to ask a question, would you raise your hand using the Zoom function, please? And then I'll notify you, and then we can point that towards Nick. Anyone?
Spencer, I don't know whether anybody else is having this problem, but I can't see a raise hand icon on Zoom.
Okay.
But I do have a question.
Perfect. Okay, you can ask a question, Rebecca. Thanks so much.
Thanks, Spencer. I thank you for the talk. It was very interesting. I don't know whether I missed it. I don't think I did. What task did you use to measure or train with visual spatial working memory, and what scoring protocol did you use? Did you use time, accuracy, combination?
For the inter-individual characteristics?
Yes. And also, what was the training?
So we had the training tasks were there were grid tasks. So they're mainly visuo-spatial working memory grid, where the subjects saw a. Are you still there? Yeah, where the subjects saw
Interesting.
where the subjects saw a grid, and then they saw a pattern, and they had to repeat this pattern in a variety of fashions, either in a square or in a circle or in a 3D cube. And then the measures that we took in the first week were the average capacity of correct trials, and then the amount of correct trials divided by the total trials as performance.
Okay, so
an interaction for was the capacity in the first week.
Okay, so there are a number of spatial locations. So, and I'm not criticizing, I'm just getting it clear. So there wasn't an explicit manipulation of the material. It was.
No, there's not an explicit manipulation.
Okay, all right. Thank you.
They had to hold the pattern that was repeated and then repeat back the pattern in order.
Okay, so arguably you could say it was a short-term memory task, even though they kind of blend short-term memory to working memory in terms of degrees of.
Yeah, I would say for working memory, it's somewhere probably in the middle.
Okay, cool. Yeah. Thank you very much.
No worries.
Yep, Raz.
Hi, thanks for the talk. I remember a talk talking before about the fact that there seemed to be the kids with better work memory who benefit more from the visual spatial work memory training. And it was interesting to see the reverse pattern for the nonverbal reasoning. And do you have any idea why it would be so different?
I really don't know why. There's very little research. I tried in nonverbal reasoning for transferring to mathematics. I tried to look into it as much as possible, but I feel like this is kind of an understudied area. If you look back at the literature, there are hints towards visuospatial working memory training being more effective for children with already high levels, but the contrast.
Yeah, there's that in the past, but I'm just wondering about the why it would be so different for nonverbal reasoning. Why it seems that there isn't the same constraint to the kids who start badly. They might kind of improve. I mean, and I think in your training curve, they kept improving for much longer.
Yeah. We should be.
We seem to plateau a bit.
We should be a little bit careful in comparing those two interactions, because there's a lot less variance in the nonverbal reasoning. So the maximum amount of time that we changed was 4 minutes, while with visuospatial working memory, we have a lot more of variance in the amount of time that they're doing. So if this would be the case, if we were to change, say, every day, if we were to change 15 minutes, remains to be seen, because we're only, again, changing for nonverbal reasoning, we're only changing 13% of the time. So it's quite little.
So you mean if they were doing more nonverbal reasoning training, that we might also see a plateau, but because they're not doing that much.
Oh, you mean in
the training curve?
In the training curves? Yeah, potentially. But I meant mainly for the interactions, for putting those interactions next to each other. They're not on the same scale, essentially.
Yeah, but it's still a completely different pattern. So it doesn't seem to be a quantitative effect. It's more of a qualitative effect, really.
Yeah, I found it really interesting. And yeah.
Nora, you have a question?
Yeah. Hey, so thank you very much for the talk, and it's wonderful to be able to join from the United States. I am curious about your thinking about spatial ability. You're using a sort of the Lohmann approach and, you know, talking about maintenance and etc. But obviously, I have my own thoughts about these typologies and how to think about spatial ability. So I have two questions along those lines. One is, why do you think the nonverbal reasoning is spatial? And secondly, about mental rotation, I fear that there's been a little obsession with mental rotation, and in a way, I'm sorry that Cheng and Mix in their small study started with mental rotation, which the field has been obsessed with, frankly. And instead, there are these other things, one of my favorites being spatial scaling, that have greater conceptual linkages to mathematics, including to the number line? So those are my two specific questions.
So going in, I'll first tackle the nonverbal reasoning. I think nonverbal reasoning has more of a spatial background than these types of visuo-spatial working memory tasks, because by definition, you need to remember the order of different, you need to remember the order and the spatial representations of different colored blocks and patterns. And I think it is inherently a spatial task. Of course, it's tapping into reasoning. And again, all of these things kind of blend together. But I actually, if there wasn't the words visuo-spatial in front of visuo-spatial working memory, I would argue that that task is less spatial in nature. And then what was your second question again? It was, oh, it was the mental rotation. Yeah, it would be really good to put in spatial scaling, I agree. And there is quite a lot on mental rotation. Again, most of the...
Yeah, oh, sorry, just, and very, because I'm poking at mechanism here. So scaling's related to number line, which of course you're already training. So maybe you don't need to train scaling as well. Maybe scaling works against a background in which you're not training the number line. But also remember that what Cheng and Mix originally found was that mental rotation training helped one specific thing, which were those missing addend problems. And that's the one thing in which I can think, well, not the one thing, but a key thing in which it makes a difference to do a dynamic transformation. It's like, oh, that number, it goes blah, blah. So we can't necessarily look at these questions globally.
Yeah, I would agree with that. Yeah, it's tricky because we also wanted to put it into factor. We wanted to get to this like latent mathematics in the children as well. So we actually intentionally didn't test addition by itself or subtraction missing term by itself or number comparison.
No, I get it. It's the tension between doing this fine scale cognitive development, cognitive science that people like me love, and doing these incredible big studies, which is just amazing.
Yeah, it would be really cool to put in different types of spatial training rather than just mental rotation. But yeah, again, as you said yourself, the field has so much mental rotation in it. It's a bit crazy.
Thanks. Okay, thanks. Anybody else? Yep, Ross.
Yeah, I think I must have blanked out. Can you remind me what the maths test, like what you put in your maths latent factor, what task did it actually do, the children?
There were missing term addition tests, the same for subtraction. And then there were Roman numeral number comparison, and then the reaction time on that. So they would see a 6 and a 9, and they would have to tap on what was the larger number.
Why did you choose Roman numeral? That's quite, I've never really seen it before.
I think Torkel might know the answer of that question. I'm actually unaware of why that task was chosen, but I actually really liked adding it to the factor because then it got to a little bit of a difference. So with the experimental led tests, we use WISC. We use the WISC verbal arithmetic, and adding a test like that, which had quite high correlations with the addition and subtraction, it ends up making this latent factor a little bit more basic mathematics rather than just addition and subtraction.
What do you mean by basic mathematics? Like instead of arithmetic? Is that
Yeah, it's abstracting to a bit of a higher level rather than just addition and subtraction abilities. With the, if we were to put in the WISC verbal arithmetic, it's more just addition and subtraction. This is getting more to, I don't want to use the word numerosity, but it's getting a bit more generalized.
Okay, thanks. Katie?
Hello, can you hear me?
Yep, we can.
Hi, first of all, I want to say thank you. That was extremely interesting. I have two questions, and one of them ties a little bit to what Nora's question related to. So I guess in this question of mechanism, do you think it's possible that given that you were already giving everyone number line training, that part of the effect was kind of some perfect storm between the working memory training plus the number line, so essentially the two working together in combination, and actually the mental rotation in different contexts may have had a different effect? And my second question has to do with participant engagement. So did you have any sort of measures of how well the children liked these different training versions, and whether they engage with them to the same level? I know obviously in classroom-based studies, it's really hard to measure, you know, how much these different, particularly different subgroups of children are actually paying attention and doing the task by themselves, and that sort of thing. And I suppose coming to Irwaz's question a little, maybe it was the case that the children with the lower working memory, a part of what we might be seeing are attentional demands, and that maybe it's the case that they didn't adhere to the training as well.
Yeah, that could be very much the case. This was kind of like in the wild, very ecologically valid study. So we actually don't entirely know. We do know that, well, the randomization was within the classroom, and we do know the amount of time they were on that. But again, that might not necessarily correspond to how much time they're paying attention to the app. That's kind of hard to get to. And I really agree with your first point there, because one of the mechanisms of transfer for mental rotation training that's been written in the literature is that it benefits the conception of a number line. So the heavy number line training could be pretty much taking away that effect that we would have seen had we not had number line training. Because mental rotation could be honing the mental number line. And since we had number line training, this might have just run over the rotation training, essentially. Did that answer your questions?
Yes, it did. Thank you.
Sweet.
Okay. Any more questions? Yep, Miraz.
Sorry, I'm just wondering about that question, Katie's question about the engagement. Have you looked at all about, rather than the minutes of training, about how many trials they did?
Yeah.
I guess you would hypothesize that a child who's not engaged, that could also be they're struggling, but they just go more slowly through the whole thing.
Yeah, that's tricky, because also a child that there's less trials from a lack of engagement, and there's also less trials from a child that is like cognitively struggling with the tasks themselves.
So I don't think you can completely separate it, but I think it might be quite interesting. I mean, you do have a bit the starting measures, which might give you a bit of an idea of where they are on the cognitive ability level, but then how many trials they're doing during the training might give you a bit of an idea of how much they're engaging in it.
Yeah, and try to somehow differentiate between engagement and struggling, like cognitive struggling. Yeah, that would be really interesting, without a doubt. I assume the two will be quite highly correlated, just because the children that have higher baseline will be going through, like if they find something easy, they're going to be going through it much quicker.
But it was adaptive, right?
Yes, it was. So
they will end up at a level that is challenging enough for them. So in that sense, it should match a little bit how difficult it is for them. So I just wondered whether that would be a measure of engagement.
Yeah, that would be really cool to look at. I'll definitely keep that in consideration and take a look. Because it would be good to know a little bit more of the characteristics of what exactly was going on and how their engagement levels are.
Yep. Cool. Jamie?
Last point on that, you could a less engaged child may also not do the staircase very well. So that might be a bit more random, their answers. We've had that in a different study where some kids which couldn't, sometimes they get a difficult one correct and they got an easy one wrong, and it makes you feel like maybe they're just not really focusing. So I wonder whether looking at their sort of progression curves might also give you a bit of an idea of engagement. But
Yeah, especially the visuo-spatial working memory task should be a particularly good task to see, because it's so adaptive to their level to see engagement, separate engagement from cognitive performance.
Okay, Jamie, sorry.
Yeah, hi Nick, thank you. Really enjoyed the talk. I just wanted to ask a question about nonverbal reasoning generally. So in England, we have the 11+ test for kids, and I don't know if you're aware, but in private schools, they often get a lot of training on nonverbal reasoning as well as visuo-spatial tasks, whereas in state schools, it's sort of non-existent unless it's maybe dropped in by a specific teacher. And I just wondered if you could comment, do you think that might suggest, therefore, that kids in state schools might be at a little bit of a disadvantage mathematically? This might impact from the research that you've done and obviously the other studies. Do you think, could you suggest that that might have an impact on children who don't get any nonverbal reasoning at all through primary? Might they be at disadvantage?
I would say for nonverbal reasoning, that aspect of our study is much more of the experimental arm. And that could be the case, but I wouldn't be confident enough to put my name behind a claim like that. But I think it's a very interesting area of research, and I would love if there was more research in that direction. But it is quite understudied at the moment.
Thank you.
Okay, Katie, again.
Sorry, I have one other question that I thought of when Irwaz was speaking, which is, I suppose your findings in a way tie quite closely to Zach's 2015 findings, so that Hawes paper. And I can't quite remember, but maybe the Rodin paper was the same, in that the training was done on the computer. And I'm wondering whether how much of some of the transfer of gains that we see in some other studies might have to do with the fact that the children are using physical manipulatives of some sort. And I wonder whether, because I know in the Hawes paper, they were certainly in the classrooms, or at least had some teacher reports of what was happening.
Yeah, especially
in that sense. Yeah, and so they found no transfer either. And I wonder whether, you know, their training was on iPads, yours was also digital, and whether or not this is kind of adding to this literature maybe that actually for the mental rotation training to be effective, the children need to be doing some sort of, you know, physical action or embodied action with some physical materials.
Yeah, that could definitely be the case. It could be that it's embodied. So one of our tasks, again, it is on a tablet, so it's not embodied at all, but one of our tasks did require physical manipulation rather than just the 2D mental one where it was mental manipulation. I think that could be the case. I really do think that if rotation training is in this age range honing the mental number line, and that's the primary road of mathematical transfer, then that it was mainly our number line training, which could have taken that effect away from rotation.
Yeah, I think that's possible. I mean, I think if you look at kind of other studies, and the one that's coming to mind is Kelly Mix's 2020 study, where they compared spatial visualization training to a form perception or visuo-spatial working memory group, and they found that the gains were quite similar. And so I guess in that sense, it questions the underlying mechanism question for me, which is why we would see one being more effective than the other in this case, and whether or not it is this mix of the other training they were also getting.
Yeah, that could very well be the case. Again, with these active contrasts, we're looking at very, very, very small differences. So we would need quite substantial effect sizes, because we expect all of these domains to have some effect on mathematics. So in that paper, when they're comparing visuo-spatial working memory training to rotation, I mean, we expect both of them to impact mathematics. So to see such a minuscule difference of active training, we really kind of need to have at least a sample size, I would say, of 400 or 500, depending on how big, on what I would expect as a far transfer to mathematics.
Okay, cool. Corinne?
Hello, wonderful talk, wonderful design. I'm super excited about your design and the sample size to begin with. I think it's very encouraging. I'm a postdoc with Kelly Mix, and I just had a quick follow-up question. Given that your training is 6 weeks long, are you able to track, or have you tracked performance during the training, and maybe are able to separate performance on the tangram versus your mental rotation app? And because to me, it seems like your tangram app may be more complex, requires maybe more scaling, general spatial visualization processes rather than just rotation. So I just wonder if you had any idea about performance.
Yeah, so we looked at 2D mental rotation quite a lot. We we didn't look at the training curves of Tanagram. We found rotation to continue, for children to be continuously improving throughout the weeks. So for example, as a tough test on ourselves, we just entirely excluded that first week. So we took the second week to try to get rid of if there's any like task features or practice effects. And then we took the second week and we compared it to the third, the fourth, the fifth, the sixth, and the seventh, and found like quite consistent and linear increases, except in visuo-spatial working memory, which around 5 weeks, then it clearly started being less effective. But it would be cool to look a little bit more into the Tanagram and contrast these two tasks. The thing is, a priori, we considered them both as rotation. So we kind of lumped them into rotation, and then we did that one analysis to make sure that, yeah, that because one is more immersive, that there wasn't different effects going on.
Okay, thanks. Sue, please.
Hi, thanks. I find it's really fascinating. Could you say, as I'm coming from the state system, a bit more about nonverbal reasoning? I'm not clear what it involves really, or what. It seems the example that you flashed up had number in it, a number sequence. So then that would have the effect, wouldn't it, on the maths?
It didn't have a number sequence. It was from the LIDAR test battery. So it's very, very similar to matrix reasoning. It's a type of nonverbal reasoning where you see a bunch of patterns and you have to decipher, and it's essentially spatial reasoning where you have to decipher the different patterns and fill in the blanks.
So it's about pattern. It's just that I took a little screenshot and you've got a pattern that goes 6, 4, 3, and you have to put the missing ones in, which are 5 and 2 in a decreasing number pattern.
Yeah, so you could use a mathematical strategy to solve it, but most of these tasks are not necessarily mathematical in nature. So
they're about remembering orders of colors and things like that. Are they spotting patterns?
Yeah, patterns and sequences and colors. Exactly.
Right.
Very similar to matrix reasoning. But
yeah, I'm not familiar with matrix reasoning either. So.
Oh, okay. It's a classic fluid intelligence test. So it's you see these abstract patterns and you have to decipher these rules and figure out what is the missing tile.
Right. So that's very interesting from the pattern point of view of teaching children pattern spotting. That's right. Okay, that's very interesting. Thank you very much. Thanks.
No worries.
Okay, we've got 3 more minutes. Any more questions? Well done, Nick. You fended off about 20 minutes of questions there, which is brilliant. So well done. I'll just wait for 1 second until, yep, we don't have any more questions. So thank you so much for your time this afternoon. Make sure you're safe and careful in Sweden. All right, yeah. We're locked down heavy here in London, so I'll take care cycling home tonight in the dark. Okay, and thank you so much. And for those guys that attended, thank you for your time also this afternoon. We are free next week, and then our next session is on the 19th of November. So I look forward to seeing you then. And thanks a lot. So take care, Nick.
Yeah, thank you. Thank you very much.